what we're hoping to build over the course of the next hour and a half, or however long we're here, is several different methods of not only computing determinants, but also using determinants for other purposes. So actually these first two bullet points here are methods of computing determinants, row reduction and the minor and cofactor method. And the third, the adjugate, is an application of what we can use a determinant for. And these two will be things that you'll do with your group. And the first one is something that I'll tell you about presently, which is what does row reduction, the process of applying elementary row operations to a square matrix, what does that tell us about the determinant of that matrix? So I want to start with this 3 by 3 that we have up here on the board. And as a reminder, the geometric interpretation of what the determinant of this matrix A should be is it should be the volume of the image of the unit cube now in the codomain. And the image of the unit cube in a three-dimensional example is going to be a figure that looks like this, which has parallelograms that are congruent on its opposite sides. Call one of these a parallelepiped. And so the determinant of A, at least up to a sign, plus or minus sign, this determinant should tell us the volume of the parallelepiped having the three columns of this matrix as its spanning sides. So there's the first column, the second column, and the third column. So my goal is to figure out how we can find the determinant of this 3 by 3 matrix by first doing some row reduction instead. In other words, if we could row reduce this matrix down to at least its row echelon form, so that the pivots have been identified and there's only zeros underneath them, that maybe that would be enough to find the determinant of this matrix somehow. So let's first get the ugly business of row reduction over with. And let's get this matrix into its row echelon form. So starting with -2, 2, 1, 2, 1, 0, -3, 0, 2. If my first target for having a pivot is right here, then what do you want to do first? Okay, having divided the first row by -2, now we have a 1 in that first pivot position, which means that we are ready to clear out the underbrush underneath that pivot, get rid of that 2 and get rid of that -3. And what are my steps toward accomplishing that? Right. Multiply row 1 by -2 and add it to row 2. So I write that as row 2 minus 2 row 1, but you understand what that means. So that will take care of that 2 that's underneath there. And likewise, for the third row, to clear out that -3, we will add thrice the first row to the third row. And that will take care of that -3. Okay. So we know the second pivot is in this position in the middle. Now all we want to do is clear out the entry underneath that pivot. What's the quickest way to do that? I'm going to kind of break procedure here. Yeah, let's just add the two of those together. So I'm just going to add 1 of row 2 into row 3, and that will zero out the last entry that needs zeroing out. Give it a half, 0, 3, 1, and then 0, 0, 1 plus a half, 3 halves. Okay, so we've now brought our matrix down into its row echelon form. We've identified its pivots, and there they all are. So now here's a new question. Now that the matrix is in this nice simple form, is there an easier way to find its determinant? So what do the texts tell you? Yeah, the determinant of a triangular matrix. And when I say a triangular matrix, what I mean is a matrix, the entries of which beneath the diagonal are all 0. So my below diagonal entries are these entries down here. And so the entries below the diagonal are all 0, which makes this a triangular matrix. And as Catherine says, the determinant of a triangular matrix is just the product on its diagonal. In other words, that would be the product of the three numbers that we have in the boxes here. 1 times 3 times 3 halves. So the determinant of this matrix we have down here at the bottom of our list is 1 times 3 times 3 halves. 9 halves. But now I've got to ask, is it suspicious at all to claim that the determinant of our original matrix might be 9 halves? Why is that less than believable for this original matrix?
If you kept row reducing a little more, like I had 1 and 1, does it matter?
If we kept row reducing, we would change the determinant of our final answer here. But the point is that the determinant of our final answer is not the same as the determinant of our original. Because some row operations change the determinant of a matrix. Some don't, but some do. So I want to hear from your groups really quickly. We have 3 different kinds of elementary row operations that we can do to a matrix. Namely, the first is to swap 2 rows. Second is to add 2 rows to one another, or possibly subtract, but we'll say add. And the third is to multiply a row by a constant. Let's say we're multiplying it by k, or something like that. So first, group A. Yeah, your group. What did you find happened to the determinant of a matrix when 2 of its rows were swapped?
Got the negative, so when the rows swapped, you got the negative answer of the determinant.
Yeah, you get a sign flip. When you swap 2 rows of a matrix, its determinant switches sign. If it was positive, it became negative. If it was negative, it became positive. So mathematicians will say that the determinant is what's called an alternating function. That if I exchange the order of 2 rows, or if I exchange the order of 2 columns, it turns out, that the sign of the determinant switches. So that's the first thing to notice, is that swapping rows flips the sign of the determinant. Now, we didn't do any of that in the process of taking our determinant, so we don't have to worry about there being any sign flips in the work that we did. How about multiplying a row by a constant? The other group kind of looked at this, except in your group you ended up multiplying the entire matrix by a constant. You multiplied your entire matrix by 3. What happened to its determinant? Question B3 or something?
I think you multiplied by 9.
Right. So your 2 by 2 matrix, when you multiplied the whole thing by 3, the determinant went up by 3 times 3. The reason for that is that the determinant is a linear function not of the matrix, but of the rows of the matrix, or the columns, if you like to think of it that way. And being a linear function of the rows of the matrix means that if I multiply a row by a constant, that the determinant also gets multiplied by that constant. In your example, you multiplied both rows by 3, and so one of those gave you a factor of 3 in your determinant, the other one gave you an additional factor of 3, and so in total it was 9. But if we're just doing it to one row at a time, then whatever we multiplied that row by, we have also multiplied the determinant by. And that's a step that we actually did do in our row reduction. We did it here at the beginning. The very first thing we did in our row reduction was we divided the first row by negative 2. And so the question is, what happened to the determinant when we did this? Exactly. The determinant got divided by negative 2. So the determinant became the determinant divided by negative 2 at that step. And so if we want to know what the determinant of our original matrix was, we're going to have to account for this. Namely, if we want to reread this whole thing from the bottom up, because we know the determinant of the matrix on the bottom, we don't know the determinant of the matrix at the top of our list, then we should be able to account for this factor. So hang on to that for a second, and let's discuss the very last row operation. If you add two rows of a matrix. This is one that wasn't assigned to your groups, so I'm just going to give it away. If you add one row of a matrix to another row, and then store the sum in that row, that the determinant is actually unchanged. Which is good news, actually, because most of the elementary row operations that we do are of that flavor. Which means that most of our elementary row operations would not actually change the value of the determinant of A. Namely, this step didn't change the determinant, this step didn't change the determinant, and that step didn't change the determinant.
Then the -2.
The really good news is, even though we multiplied row 1 by -2 and then added, we subsequently divided that -2 back out before we kept going. And so even adding a multiple of one row to another row, as long as the row that we're multiplying stays the same as it was before, the determinant will stay the same as it was before. So all of those, the second, third, and fourth steps of our row reduction here are all of that flavor. And so they're not changing the determinant of our matrix. So the only place that our original matrix's determinant changed was here in this very first step. It got divided by -2. So tracing everything backwards, if the determinant of our final answer matrix here was 9/2, then what must the determinant of the original have been? If this determinant was D, then D multiplied by -1/2, which is what happened right here, equals the determinant that we got, 9/2. So to go from the bottom up, we just need to undo that change in the determinant that we saw right here. In other words, let's multiply our answer by -2. Solve this equation for D, in other words. And we find that the determinant of this matrix should be -9. That should mean that the volume of this parallelepiped spanned by these three vectors should be, up to a sign anyway, equal to our determinant. So the volume of that parallelepiped should be 9. Hopefully, that is the case. Yep. Cool. And the reduced row echelon form of this matrix, if we had finished, so this was Zach's question, if we kept going in our row reduction, then eventually the reduced row echelon form would have just been the identity matrix. Why? Because what kind of a matrix is A? It's a square matrix.
Invertible.
It's invertible. Its determinant was not 0. So it's invertible, which means that its reduced row echelon form has got to be the identity matrix. But doing that would have required more steps of row reduction to happen, and we would have had to account for all of those additional steps of row reduction in the determinant.
Should you just stop at getting all three pivots? That way you don't have to go so much.
Exactly. The fewer row reduction steps that you have to do, the better. And so my recommendation would be to stop where we stopped, which is as soon as your matrix is triangular, as soon as you've got all the pivots and only zeros underneath them, take your determinant there. And then just retrace the steps that it took to get you there, and you'll find the determinant of your original matrix.